When first hearing about the SR-72, many thought it was just a far-fetched concept, but gradually the leaked information revealed that Lockheed Martin was indeed working on something revolutionary. Has the next generation of American aviation been quietly born? This video is purely a technological analysis. It does not endorse any conflict or violence. SR-71 Blackbird, the pinnacle of strategic reconnaissance aviation. Developed during the geopolitical tension between two superpowers in the Cold War era, the SR-71 Blackbird was the result of Lockheed Martin's famed Skunk Works program. The initial goal of the project was to create a reconnaissance vehicle capable of rapid deployment, operating at altitudes beyond the reach of contemporary air defense systems, while ensuring maximum safety for the crew. The SR-71 featured an iconic and advanced design for its time. A long, slender fuselage, a needle-shaped nose, delta-shaped swept wings, and two powerful Pratt & Whitney J58 jet engines, designed to sustain continuous operation in supersonic environments. With an estimated top speed of around Mach 3.2, more than 3 times the speed of sound, and a ceiling of up to 85,000 feet, this aircraft could complete reconnaissance missions without relying on any offensive weapons. Operating at such altitudes and speeds imposed unique physiological challenges: low pressure, extreme temperatures, and the risk of unconsciousness from oxygen deprivation, forcing pilots to wear suits equivalent to those used in space missions, including high-pressure oxygen masks and thermal insulated clothing. Notably, the SR-71 was considered one of the first aircraft designs to apply stealth principles, before the concept of stealth became a standard. Its surface was coated with a special black paint containing ferrous iron, capable of absorbing radar waves and efficiently dissipating heat to reduce infrared signature. Furthermore, the aircraft's structure was optimized to lower radar cross-section, RCS, thus enhancing its ability to evade detection in sensor-dense environments. Technical structure, pioneering design and material foundation. The SR-71 stood as a clear example of advanced material applications in military aviation. Because it had to operate at supersonic conditions for extended periods, most of the aircraft's structure, around 85%, was made from titanium alloy, a metal known for its high strength-to-heat ratio, corrosion resistance, and suitability for extreme temperatures generated by air friction. The remaining parts of the fuselage used composite and ceramic materials to reduce weight and increase localized strength. A distinct design feature was that the aircraft's outer skin wasn't flat but constructed in a rippled form, an optimal solution allowing material expansion without cracking when temperatures rise during flight. The SR-71's windshield was also a remarkable engineering feat, consisting of 3 layers of heat-resistant glass cooled by a specialized liquid circulation system. The navigation windows were made of quartz crystal, a rare material in aviation due to its high light transmission and much greater heat resistance compared to regular glass. Additionally, the SR-71's fuel was modified for both performance and stealth. JP-7 fuel, a specialized high flashpoint fuel, was used to prevent explosions caused by frictional heat. Notably, this blend included a small amount of cesium to reduce the infrared and radar signature of engine exhaust, while also stabilizing combustion in the supersonic engine chambers. The aircraft's fuel tanks were even designed to leak under control at ambient temperatures due to titanium contraction, and would only seal completely once the aircraft reached its operational heat, a design seemingly flawed but actually a precise calculation for the supersonic environment. End of operational cycle and historical role of the SR-71 Blackbird. Although the SR-71 Blackbird was recognized as one of the most advanced aviation platforms ever developed for strategic reconnaissance, its operational life eventually came to an end. The main reason for its retirement was the operating and maintenance costs exceeding the program's financial capacity. With complex maintenance requirements, specialized fuel consumption, and a technical system demanding highly skilled personnel, the SR-71 became a difficult asset to sustain as the defense budget aimed to optimize investment efficiency. In 1989, the U.S. Congress officially decided to terminate all SR-71 flight operations within the Air Force. However, 2 aircraft were still used by NASA for research on aerodynamics and high-speed material technology until 1999. Afterward, these planes were transferred to aerospace museums, where they became historical exhibits marking a significant chapter in the development of strategic aviation technology. Although the aircraft was retired from active duty, its legacy continued to shape the next generations of aerospace innovation. Many of the technologies technologies pioneered by the SR-71, including advanced engine thermal management, radar cross-section reduction techniques, and high-altitude flight systems, were later applied in stealth aircraft programs such as the F-117 Nighthawk and the B-2 Spirit bomber. Moreover, the SR-71's success served as a proof of concept for speed as a shield, fundamentally influencing how military strategists viewed survivability in hostile airspace. The data collected from thousands of missions conducted over hostile territories, including the Soviet Union and the Middle East, provided invaluable intelligence that helped shape U.S. foreign policy and military planning during the Cold War. Despite its retirement, the mystique of the SR-71 continues to inspire aerospace engineers, aviation historians, and the general public alike. Its unmatched combination of speed, altitude, and innovation turned it into more than just a reconnaissance platform. It became a symbol of American technological ambition and engineering prowess. Development direction of the next hypersonic generation. Although decommissioned, the SR-71 left a notable gap in high-altitude, high-speed strategic reconnaissance capabilities, an area where replacements were not easily found. According to some technical assessments, during its operational lifespan, the SR-71 completed thousands of missions without ever being shot down, despite being tracked by thousands of surface-to-air missiles, a testament to the effectiveness of the speed is defense strategy. Since the early 2000s, in response to the trend of high-tech conflicts and the demand for rapid response in geopolitical airspace, Lockheed Martin's Skunk Works team began developing a roadmap for a new aviation platform, dubbed the successor to the SR-71. The SR-72 project was thus born, with a design philosophy focused on hypersonic speed, artificial intelligence integration, and flexible deployment capabilities in high-risk environments. From 2006 to 2007, Lockheed Martin collaborated with Aerojet Rocketdyne, a leading firm in jet propulsion technology, to begin research on the scramjet engine, supersonic combustion ramjet. This core technology aims to achieve flight speeds exceeding Mach 5 without the need for traditional turbine systems. Scramjets promise quick access to critical zones and reduced tactical response times, aligning with deterrent strategies in new generation conflict environments. TBCC propulsion system, a leap in hypersonic engine technology. One of the core elements enabling the SR-72 to fly at hypersonic speed is the use of the TBCC turbine-based combined cycle propulsion system, a technical solution that integrates two engine types with completely different operational characteristics. The TBCC system allows flexible switching between turbine engines, suitable for takeoff and landing phases, and scramjet engines, designed for hypersonic flight within the atmosphere. The TBCC configuration overcomes the weaknesses of using each engine type independently. Specifically, at speeds below Mach 3, the jet turbine operates efficiently, providing stable thrust and control. When the aircraft reaches the required velocity threshold, around Mach 3 to 4, the system shifts to scramjet mode, allowing fuel to burn within airflow moving at Mach 3 to 4 supersonic speeds, thereby maintaining and increasing speed up to Mach 5 to 6. To ensure continuity and efficiency during the transition between these two operating modes, engineers designed an integrated intake and exhaust system, shared by both engine types, but optimized to direct airflow through separate channels compatible with each flight phase. This design requires extreme precision and thermodynamic control to maintain performance and ensure structural safety for the entire propulsion system. Heat-resistant materials, a key challenge in hypersonic aerodynamic design. One of the greatest challenges in achieving sustained hypersonic flight, Mach 5 to 6, is managing the heat generated by aerodynamic friction. At these speeds, the temperature in airflow leading regions, such as the aircraft's nose, wing edges, and air inlets, can exceed 3,500 degrees Fahrenheit, around 1,927 degrees Celsius, enough to melt most common metals like aluminum or stainless steel. To solve this issue, designers turned to materials capable of withstanding extreme heat while remaining stable stable under harsh mechanical conditions, among them carbon ceramic matrix composites, CMCs, and ultra-heat-resistant alloys, previously used in ballistic missile and space shuttle programs, have been studied for application in the SR-72's body and nose. Beyond heat resistance, these materials must also meet essential requirements such as lightweight properties, oxidation resistance at high temperatures, and structural durability under significant dynamic pressure. This is one of the most heavily invested areas in aerospace materials technology, as success in designing the SR-72 could pave the way for numerous military and civilian applications in the future. Official development statement and new design philosophy: speed is the new stealth. In 2013, Lockheed Martin officially confirmed the existence of the SR-72 project and announced the development of an aviation platform capable of flying at hypersonic speeds of up to Mach 6, which is twice as fast as its predecessor, the SR-71. This declaration marked a major milestone, not only for restarting the high-speed strategic reconnaissance program, but also for introducing a completely new design philosophy. Speed is the new stealth. Unlike stealth vehicles that use geometry and radar-absorbing materials, the SR-72 is designed to utilize hypersonic speed as a method of minimizing detection and reaction by ground-based defense systems. When an aircraft can pass through enemy airspace in just minutes, it significantly degrades the effectiveness of traditional radar and missile defenses, a noteworthy alternative in an age of increasingly advanced surveillance systems. Lockheed Martin also emphasized that the SR-71 was a product of 20th century technology, while the SR-72 is designed and developed using the technologies of the digital age, including big data, digital simulation, and modern physics analysis. One of the key supporting data sources comes from the HTV-2 Hypersonic Technology Vehicle 2 testing program, an unmanned hypersonic flight platform funded by DARPA that reached speeds close to Mach 20 in prototype tests. Bringing technology from theory to practice, SR-72 implementation progress. In 2016, the CEO of Lockheed Martin declared that the SR-72 project had come very close to reaching a viable stage in terms of manufacturing technology. Accordingly, the first SR-72 prototype was expected to be similar in size to the F-22 Raptor, a design that allows for flight testing and performance assessment in real-world conditions while optimizing research and production costs. One notable point is that the budget target for the SR-72 prototype was set at under $1 billion. A figure considered relatively modest given the complexity of the TBCC system, the ultra-heat resistant materials, and the unique aerodynamic requirements. By 2018, Lockheed Martin's vice president continued to affirm the project's positive progress. He stated that thanks to the development of technologies such as high-precision metal 3D printing, supercomputer-based dynamic simulations, and digital design technology, many technical barriers once thought insurmountable had gradually been overcome. These technologies not only shortened the prototype development timeline, but also significantly reduced production and testing costs, thereby advancing hypersonic theory into practical application. In addition to technological breakthroughs, Lockheed Martin also benefited from increasing cooperation with defense research institutions and government agencies. Collaborative testing with the U.S. Air Force Research Laboratory, AFRL, and DARPA provided vital data on propulsion materials and system integration that helped refine SR-72 design iterations. Furthermore, the project's alignment with national hypersonic development priorities allowed for a more streamlined path through regulatory and budgetary approvals. This level of integration between military vision and industrial execution has been cited by experts as a key driver in maintaining momentum for the SR-72's progress. As the program enters its advanced engineering phase, the focus has shifted from foundational R&D to prototype validation and pre-flight integration. The ultimate goal is to demonstrate a fully functional test vehicle capable of sustained Mach 6 flight, a milestone that would mark one of the most significant achievements in aerospace engineering in decades. Integrated strategic weaponry, hypersonic missile deployment capability. One of the strategic directions for the SR-72 is its ability to integrate and deploy high-speed weapons, particularly hypersonic missiles. This is a trend being pursued by many countries to enhance combat effectiveness in next-generation conflict environments, where speed to target and air defense penetration are key. Although launching weapons from a platform traveling at Mach 5 to 6 presents challenges in aerodynamics, targeting, and flight stability, lessons from history provide a technical foundation for this capability. Specifically, in the 1960s, Lockheed successfully tested missile launches from the YF-12 aircraft, a weapon-capable variant developed from the SR-71 Blackbird's design. These early tests, though experimental, laid the groundwork for evaluating technical aspects such as signal delay, stable mounting structures, and target tracking accuracy at high speeds. For the SR-72, integrating hypersonic missiles is not only a technological breakthrough, but also a crucial element that expands the platform's strategic use, from pure reconnaissance to precision strike deterrence in short response times. Additionally, the inclusion of such weaponry enables the SR-72 to perform roles beyond surveillance, including strategic first strike missions in contested regions. The aircraft's speed offers a significant tactical advantage. It can deliver a missile strike within minutes, even before enemy systems can fully respond. This preemptive capability, when combined with advanced AI-guided targeting and stealth flight profiles, gives the SR-72 potential to serve as a next-generation deterrent in future warfare. Integrating these systems requires cutting-edge synchronization between onboard guidance systems and external targeting networks, such as satellites and drones. Lockheed Martin is reportedly developing secure, real-time communication protocols to ensure missile accuracy even at extreme velocities and distances, pushing the limits of current aerospace command and control infrastructure. Presence in popular culture and international misunderstandings. In reality, the SR-72 is still under development and has not yet been publicly revealed. However, the image of an aircraft with a similar design unexpectedly appeared in the film Top Gun: Maverick 2022 under the name DARKSTAR. This aircraft was the result of a collaboration between the film's production team and engineers from Skunk Works, the division of Lockheed Martin specializing in advanced aerospace technologies. Although created for artistic purposes and not representing an official design, DARKSTAR attracted special attention from international observers. According to some sources, foreign intelligence agencies, including China, reportedly deployed spy satellites to film the studio area, suspecting that it was the real prototype of a secret US Air Force aircraft. This event shows the level of attention hypersonic platforms like the SR-72 are receiving, not only within the defense industry, but also among the global public. At the same time, it reflects the increasing overlap between defense technology and popular imagery, where advanced technology concepts no longer remain in labs, but also spread into culture and mass media. More than just a movie prop, DARKSTAR sparked debate in defense forums and aviation communities worldwide, prompting speculation about the real status of hypersonic projects. Analysts noted that even fictional representations can inadvertently reveal core design philosophies, such as engine intake shapes, fuselage contouring, and materials placement, offering clues to adversaries and enthusiasts alike. The convergence of defense R&D and pop culture, as illustrated by DARKSTAR, marks a new era where national security, entertainment, and public perception intersect. In this environment, managing the narrative around experimental technologies becomes as important as engineering them. SR-72, Prototype Flight Timeline, Expectations and Reality. According to previously released information, the experimental prototype of the SR-72, a next-generation hypersonic reconnaissance aircraft, was expected to perform its first flight around 2025. However, given growing technical challenges and the need to optimize budget usage, this timeline has now been adjusted to between 2027 and 2029. This period is seen as necessary to ensure critical technical components, including the TBCC engine system, ultra-heat-resistant materials, and flight control technology, reach sufficient maturity for real-world operation. It is worth noting that the SR-72 project has now been officially incorporated into the US Air Force's Hypersonic Platform Development Roadmap. This inclusion helps secure priority in budget allocation and resources, as well as officially establish SR-72's role in the long-term defense technology modernization strategy. However, the cost of development remains a factor that cannot yet be precisely quantified. With technological technological demands beyond conventional limits, especially in materials, high-precision control systems, and AI integration for automation. The actual program budget has not been publicly disclosed. This is understandable, as high-tech projects often involve variable costs depending on research progress, technical risk levels, and shifts in strategic direction. Whether the SR-72 can enter test phase within the next 5 years will largely depend on the ability to maintain budget commitment, achieve technology milestones, and secure successful outcomes in related programs, such as scramjet engine trials, high-speed navigation technologies, and resilience against prolonged hypersonic conditions. Can the SR-72 truly follow in the footsteps of the Blackbird? And when will we see it soaring through the skies? Share your thoughts. If you enjoyed the video, don't forget to like, subscribe, and hit the notification bell so you won't miss any of our upcoming content. This video is purely a technological analysis. It does not endorse any conflict or violence.